So, last lecture we left the double cone to decide is it a surface or not. Now, for this particular lecture series, we will be concerned about not all surfaces, but regular surfaces. So, let us make things a little bit formal. So, first of all, we have defined what is a surface. Surface is subset of R3 and for any point P in S, we are recalling there exists U in R2 open, look at your last lecture notes, and W in R3 open, P containing W, P is in W, and a homeomorphism sigma from U to S intersection W. And we may need more than one sigma to cover S, as in the example of S2, the sphere. More complicated surfaces will need more and more sigma. So, this S and collection of sigma, this collection is called, so this collection comes with U, W, etc., is called an atlas for S, and the sigma is called a surface patches actually, because we need more than one sigma. So, examples we have done: plane, we can cover it by one surface patch, we have done example of sphere, which is covered by two surface patches, in cartographic sense. If it is not clear that how we arrived at it, think over it again. I will do it again, no problem. More general example is, suppose I have a f from R2 to R, a smooth function. What is a smooth function? That is fx, fy exist and differentiable up to any order such a thing as a smooth function, and if I look at graph, you remember we did it for the curves also. Now, what is smooth about smooth surface? Here also I have taken smooth function. Here this sigma uv is smooth map, sigma 1, sigma 2 is smooth map. So, what I want for smooth surfaces that this, so what is the parameterization here? Here the sigma uv is uv fuv. So, in all this example I want sigma to be smooth map, and regular, by regularity I mean sigma u cross sigma v, this is the cross product, this is not equal to 0 at all P in S. Why do you need this? This is analogous to what we did in the curves case. You will see very soon in next or next to next lecture. This means that the surface has well defined normal at each point. I give you more examples to work you out, and I will be coming back to examples, and maybe some of them I will be working out in very details. Equal to 1, okay, 1 is standard one, where A, B, C all not equal to 0. This is called an ellipsoid. If A equal to B equal to C, then I will got to get a sphere. Then there is torus. How do you generate a torus? Okay, let me do it here in the board, on the board. So, you take a circle, let us for sake of convenience, I take the circle on xz plane. So, circle has radius b, this is z axis, the distance from the center of the circle to z axis is a, and I rotate this fellow. We will come back to this kind of example more and more, but if you move to any other courses from here, this torus will come back every time. So, this is one of the first example where it will come, it is very basic example of differential geometry, and another I will do at the end. So, what do we do here? I take a circle, I have a line which does not intersect the circle, and I rotate the circle around that line. I have a circle on the plane, a line in the same plane, and I rotate it around z axis, around the line. For convenience here I have taken z axis. So, what will be the picture? So, a particular point here will move like this, particular point here will move like this. So, the final picture you will get is something like, so this is a standard way of, this is one way, I mean this is a way people draw torus. you will see in many maths book that let this be a torus. What they mean is that we have a axis, exactly this, we have an axis, we have a circle in the plane and we are rotating the circle around the axis. So, you should view it from the above. Such a thing is torus, and for this particular one the parametrization, I mean the surface patch is so if you cannot do it, we will do it anyways, we will do it in next to next lecture, but for time being find theta and phi. Theta and phi in terms of, remember, if I have a particular point on a surface. So, let me draw the torus here. This is surface. So, particular point here P, project it on the xy plane, theta is this angle and pi is the angle between x axis and z axis. Okay. Now, as we have seen, in the case of sphere, that we need more than one surface patches to cover the entire sphere. For example, recall S2, okay, I can, yeah, here it is. I need more than one surface patches, and here there are many points in so I put an exercise there. What are those? So, what are the points which are in the intersection, but you will see there are many points. Okay, let me answer this question here. What is sigma u? Sigma 1 u. Sigma 1 u, this will be, so check. This is complement of great circle C consisting of the points on S2 in the form okay, and sigma 2 u, check again, complement of dot 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 great circle C1 consisting of points on S2 in the form x y 0, x greater than less than equal to 0. So, there are many points in the intersection. So, in general, if I have two surface patches sigma u from a surface for a surface and sigma tilde from another u tilde, and P is a point which belongs to S intersection W tilde, then I can take V to be sigma inverse which is subset of U, and V tilde sigma tilde inverse subset of U tilde, and then I have a map sigma inverse compose sigma tilde from V tilde to V, which will be an homeomorphism again. Why it is homeomorphism? Think about it, otherwise ask it in the forum. Everything homeomorphism here. So, this map will be homeomorphism, and this map is called the transition map. Actually, it will be transition maps because a surface usually comes with many surface patches, and it can be, I will use the word reparameterized with another surface patches. So, there will be many transition maps. So, given an atlas, I will have given two atlases between regular smooth surfaces, I will have transition maps. And what I need here, that we need a theorem here, that since we are talking about regular smooth surfaces, the transition maps of regular smooth surfaces are smooth. This is the first theorem I wrote down for the surface this week's lecture. I will not give the proof. I say the proof will be posted in the forum, because this uses so called IFT2, which is inverse function theorem, which is an application of implicit function theorem, which I talked about in the introduction of the course. And perhaps I will need another theorem here, that how transition maps arise. This is a converse to the above theorem, that suppose U and U tilde in R2 are open sets, and sigma from U to R3 is a regular surface patch I have a map phi from U tilde to U, which is bijective, that is 1 1 1 2 smooth, with smooth inverse phi inverse from U to U tilde. Then sigma tilde phi compose phi from U tilde to R2, sorry, I should have R3, no? Is a regular surface patch. This proof will be also posted. I do not want to bother you with the proof in this course, but to just give you the idea. So, these two theorem actually leads you to something. Leads you to what? Let me summarize it. That when you are looking at surface, we are looking at locally. When you are looking at locally, then I can consider this a local portion where I am concerned with, because we will be finally looking at the surface very locally, because we look at the surface from the plane and we can see some point and around. So, instead of saying that okay, we have an atlas, but I am not moving through the atlas, I am fixing on a, I am standing on a particular open set U which maps to a particular patch of the surface, and for me that is the surface. And what I can prove for this patch, I can prove for the entire patch, provided my transition maps are smooth, that is you are standing somewhere else and we have intersections and we look at the same point, you looking at from the some other open set, I am looking at some other open set, we have intersection in the surface. Whatever we infer of the surface, they should be same. What these two theorems actually tells you, that okay, as long as my surface is regular and smooth, I should be defining the properties of surface in a way that it should be invariant under what I see and what you see. So, any properties of the surface should be defined which are invariant under transition maps. For instance, here as you see, what are the transition maps here? Transition maps here, what is the phi here? Phi is actually sigma inverse compose sigma tilde, as we done in the last page. And conversely, any such phi, here also you can see phi is sigma inverse compose sigma tilde. So, this is the way this two theorem guarantees that the properties of surface as well as the transition maps are smooth. I can define invariant of from where I look at, because surface are living in R3 and I am looking from R2. So, this is the viewpoint we will take for the rest of the course, and next time I will give an example. I will start with an example to define one property of surface called as how do you define maps between surface, smooth maps between smooth surfaces. Okay. So, that is it for this lecture. So, wait for the next lecture. Thank you.